Now we'll study the logical agents. So we actually move from reflex to reasoning. Humans know things, and what they know helps them do things. AI aims to replicate this ability using knowledge and reasoning to act intelligently. Unlike reflex-based systems, knowledge-based agents represent the world internally, reason about it, and decide what to do next. These agents don't just react, they think, infer, and adapt. So what are the limitations of simple problem-solving agents, which we studied earlier in chapters 3 and 4 of the book? They had very limited knowledge. Their transition models were hidden inside code and could not express general truth, such as, let's say, two tiles can't occupy the same space, some slates are unreachable. For the 8-puzzle problem, they worked, but they could not reason flexibly or describe complex, partially observable worlds. We need a richer way to present or represent knowledge. And then we are moving toward logic and representation. To overcome these limits, we move to logical representations expressing knowledge as facts and rules and can be combined and recombined. This enables agents to accept new goals dynamically, learn or to be told new knowledge, and adapt to environmental changes. This chapter introduces logic as a foundation for knowledge-based reasoning, starting with propositional logic before moving to first-order logic later. So what is a knowledge-based agent? The core component is the knowledge base, a collection of sentences that describe facts about the world. These sentences are written in a knowledge representation language. Some are axioms taken as given truths. We'll see some of them. Like in the beginning, you say, okay, this is given as a truth, and based on that, you perceive the world and update your knowledge. Agents interact with their knowledge base through two key operations. Okay, so one is tell and another is ask. So tell is add new information from perceptions or outcomes. Like I watch the world, get some perception through my sensors, and I update the knowledge base about those perceived information. And also I can ask the knowledge base, query the knowledge base to decide what to do next. And then I do one of those actions. And after I have done, the state of the world has probably changed, and I update the knowledge base with the changes. They rely on inference, deriving new facts logically from what's already known. So how the knowledge-based agents works, one more time. Each time the agent perceives the world, it tells the knowledge base what it perceived. It tells the knowledge base what it perceived. It asks the knowledge base what action should be taken. It asks the knowledge base about what action can be taken. And after it has taken one of those actions, it tells the knowledge base what action actually performed. Okay? So the inference engine reasons about states, actions, and outcomes, deciding the best move based on the current state of the knowledge or the knowledge base. Functions like make percept sentence or make action query. See, make percept sentence or make action query and make action sentence handle this translation between sensors, reasoning, and actuators. So reasoning at the knowledge level, we can decide such agents at the knowledge level by what they know and what goals they pursue, not by how they are implemented. For instance, if a taxi agent knows the Golden Gate Bridge connects San Francisco and Marine, it will plan a route across it, regardless of how its internal data structures or algorithms work. This separates knowledge representation from implementation, allowing flexibility and explainability. Also, there are different types of knowledge. Two ways to build such agents. One is declarative approach, in which we tell the agent what it needs to know, like facts and rules. Another is procedural approach, hard-coded behavior directly into programs. In practice, intelligent agents systems combines both. Declarative knowledge can even be compiled into faster procedural code. Looking ahead, knowledge-based agents from the foundation for reasoning systems in AI. They are the foundation of the reasoning system. In the following sections, we'll explore logic and apply propositional logic to build reasoning agents. One example will be the Wumpus World example. We introduce the Wumpus World, a small grid-based cave where an agent must survive using reasoning and not reflexes. It's a test bed for knowledge-based system, helping us see how logic and inference led to intelligent decisions under uncertainty. The environment, which is a 4x4 grid of rooms connected by passageways, some rooms have bottomless pits. One room has a Wumpus, which is a deadly monster. One room may contain gold. The agent's goal is to find the gold and escape alive. We can define the Wumpus world using a P's framework, which is performance, environment, actuators, and sensors. The performance measure says there's a plus 1000 point for escaping with gold or climbing up with gold, and minus 1000 point for dying in a pit or being attacked by a Wumpus. -1 per move and -10 for firing the arrow. So the arrow goes in the direction the agent faces, and either if it hits the Wumpus, it will kill the Wumpus, and then it emits a scream which can be heard from anywhere in the grid. If the arrow does not hit the Wumpus, it hits the wall and becomes useless. So the environment, as I said, it's a 4x4 grid, and the agent starts at location 1, 1, which is this, the first cell, facing right. Pits appear in the entire 4x4 grid randomly with probability 0.2. Actuators are the agent for the agent that it can move forward, turn left or right, grab the gold, shoot an arrow, and climb up the square 1, 1. So the agent, if it grabs the gold, it has to retrace its step or find some other way to come back to step 1, 1 and then climb up from here. It cannot climb up from anywhere else. So the sensors are 5 sensors. One is all are 1 bit. The stench, there is a stench near the Wumpus, and the stench will be perceived in the adjacent cells, not the diagonal ones, just the adjacent non-diagonal cells. There will be a stench. If they are near a pit, there will be a breeze in the adjacent cells which are non-diagonal. Glitter will be from the gold in the same square in which the gold resides. If the agent hits a wall, there will be a bump. And if the Wumpus dies, it will emit a scream and the agent can hear it from any place. These perceptions arrive as lists like stench, breeze, none, 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 if there is a stench and a breeze in a particular cell. So like let's say the cell in which gold is there, there'll be stench, breeze, glitter, and none, none. That means these 3 percepts are present. So how is this environment in nature? So the environment is discrete because it's grid-based, limited actions and percepts. It's static because the world doesn't change unless the agent acts. It's sequential because the decisions build on previous ones. We'll show it later that based on the previous knowledge, the future decisions will be executed. It's a single agent environment, only the agent acts, the Wumpus doesn't move. Partially observable because the agent can't see everything, must infer danger from percepts, and goes cell by cell. So logical inference is essentially to act safely under partial observability.